In this video, I'll go over question 4 in exam 3. A block of mass 6.0 kilograms is pushed a distance of 5.00 meters along a 30.0 degree rough inclined plane with an applied force along the incline of 50.0 newtons. The force of friction between the block and the surface is F sub k equal to 17.8 newtons. In Part A, we're asked to write a full conservation of energy statement for the block, assuming the block starts from rest and ends moving with some final velocity. Don't put in any numbers, but do indicate if any of the terms are zero. Put a line through them. Okay, in this problem we have a pushing force F sub p shown on the diagram. We also have acting on the mass a gravitational force acting vertically downward. And we also have a friction force that's given. And since the block is pushed up the incline, is moving up the incline, the friction force is going to be in the opposite direction as the pushing force. If we write a full conservation of energy statement, we'd express it this way. We have the work that's being done by the pushing force plus the work that's being done by the friction. That way in this sense, we're treating the friction force as an external force acting on the mass Earth system. And this affects the change in the kinetic energy of this system and the gravitational potential energy of this system. We can write this explicitly this way. The work done by the pushing force is F sub p, the dot product of that force with the displacement 5 meters. Is in the same direction as the pushing force. So we don't have to have a factor of a cosine theta in this definition of the dot product. It's just simply F sub p times d. And similarly, the friction force acts over the same distance d, but in the opposite direction as the displacement. And this causes a change in the kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. This term is 0 because it's starting from rest. And then we have the final potential energy, which would be if its vertical position changes by distance h, its final potential energy will be mgh. And its initial potential energy will be mgy0, which we can set equal to 0. And that's a complete statement. Although we could write it in a different way if we assume the friction or the sliding surfaces between the mass and the incline are all part of the same part of our system, then we would say that the friction force acting inside our system as an internal force is tending to increase the thermal energy. And if that's the case, then we would write our energy statement as 1/2 mv final squared plus mgh plus this increase in the thermal energy, where change in E thermal energy is equal to plus F sub kd. So that's part A of the system. If you had just written this first equation, I would have given you full credit for this part of the problem. In part B, we're asked to find the work done by the pushing force, which they tell us is 50 newtons. So that's just simply the dot product of the pushing force with the displacement, which is then simply 50 newtons times the displacement, 5.00 meters, which is equal to 250 newtons. That's part B. Part C, the change in the thermal energy is equal to the magnitude of the dot product of the friction force times the displacement. And the friction force, they tell us, is 17.8 newtons. Times the displacement, 5.00 meters. And when you multiply that, you get 89.0 joules. And then finally, part D, use conservation of energy to determine the final speed of the block, v sub f. We're going back to our statement above. The work, W sub p, which we've already calculated, is equal to 1/2 mv final squared plus mgh plus the change in the thermal energy. If we look at the geometry of this change in position, this is 30 degrees. H is the opposite side of this right triangle, and D is the hypotenuse of this right triangle. So the sine of theta is equal to H over D. So H is equal to D sine theta. So now I calculate the kinetic energy. 1/2 mv final squared is equal to the work done by the pushing force minus the change in the gravitational potential energy, which is mg times d sine theta, minus the increase in the thermal energy, which we've already calculated. So V final squared let's go ahead and take the square root. V final is equal to the square root of 2 times the work by the pushing force minus mgd sine theta minus the change in thermal energy divided by the mass. So we put in the numbers. 2 times the pushing work minus m. What was m? Let's look that up. 6 kilograms. Times g times the sine of 30 degrees minus the increase in the thermal energy, 89.0 joules, and divide that by 6 kilograms. We put that in our calculator and we get 2.16 meters per second. I realized after reviewing this that I left out the factor D in the second term. I should have had D in here. With that in there, we get the final velocity, 2.16 meters per second.